Hello and welcome to this lecture in the course for Secure Systems Engineering. So in the previous lectures, we had actually looked at one particular vulnerability in programs, especially in C and C++ programs. And that vulnerability was caused due to buffer overflows in the stack. So what we seen was that an attacker could use this buffer overflows to inject code into a program and then force that particular code to execute. So we call this as the subverting of the execution and then the execution of the payload. And then in the previous lectures, we had also seen a couple of ways where this buffer overflow type vulnerabilities could be prevented. Essentially, we discussed a couple of countermeasures for the buffer overflow vulnerability. In today's lecture, we will look at another vulnerability based on buffers. Here we are going to discuss about buffer overreads. So let's start with a small example of what buffer overreads is. So let us start with this particular example. So this particular program defines two global arrays. One is known as some data, which is initialized to some arbitrary string, and another array which is secret data, which is initialized to top secret. Now in the main function, there is a len defined, which essentially is the command obtained from the command line argument. The first command line argument is converted to an integer and it is used to initialize len. And then we have this while loop over here, which prints characters of some data. The number of characters that gets printed depends on len, and which in turn is specified by the user of this program in argv1. So there are two critical aspects in this particular program in order to understand the vulnerability of this program. Firstly, the user of this program can specify how many characters of some data he needs to print. If len is less than the size of this particular string, then there is no problem, and a few characters and at most all the characters of some data would get printed on the screen. However, if the user specifies a very large number for len, then these some data characters would get printed, as well as the adjacent characters stored in the memory would also get printed. In this particular case, the adjacent memory contains top secret. So if the value of len is large, then not only is some data printed, but also top secret gets printed on the screen. Therefore, when we actually run this particular program, we compile it as usual and run it in the command line over here and specify as command line argument as 22. So len gets initialized to 22 and it prints 22 characters starting from some data. So what gets printed on the screen is not just some data, but also the adjacent characters top secret. So this we see is a very simple example of a vulnerability due to buffer overreads. What has happened here is that the array has been initialized to some specific size, but the user has managed to read more data than is required, and essentially it's not just the array that gets printed on the screen, but memory adjacent to that particular array would also get printed. So now if we look at the countermeasures that has been presented in the earlier lectures, we had actually studied the use of canaries, the W XOR X bit, as well as ASLR, address place array layout randomization. With respect to buffer overreads, what we see over here is that the canaries and the W XOR X bit will not work to prevent buffer overreads. This is because the canaries essentially look for changes in the stack, and with the buffer overread, we are not writing or changing anything on the stack, but we are just reading the contents of the stack. Similarly, with the W XOR bit protection mechanism, we are not going to execute anything from the stack, but rather, since we're just reading from the stack, therefore the W XOR bit countermeasure will also not work. Now the third countermeasure that we have studied, the ASLR or the address space layout randomization, will also not help to prevent the buffer overreads. Essentially, the reason is that we are restricting ourselves to reading from the stack or from a given segment of memory. Now ASLR was useful to actually randomize the location of libraries, therefore making attacks such as the ROP attack more difficult to actually mount. Over here, on the other hand, since we are restricting the overreads to within a particular memory segment, therefore the ASLR countermeasure will also not work to prevent the attack. Now, let us take one particular example of a buffer overread attack. So this particular attack is known as Heartbleed. So it was a malware that was introduced in 2012 and it was disclosed in 2014. So the CVE for the malware is over here, CVE 2014-0160. And this particular malware essentially used a buffer overread to steal critical information from a web server. So the target was an OpenSSL implementation of TLS. So TLS is the transport layer security. Now this particular OpenSSL library is widely used essentially when you want cryptography or security in your web server applications. So the TLS, or the transport layer security, defines a crypto protocol for secure communication. It is widely used for applications such as email, web browsing, voice over IP, and instant messaging. It is used to provide both privacy as well as data integrity. Now, what we will discuss in this particular lecture is one particular vulnerability in this OpenSSL implementation, which had got exploited by attackers to steal information. The vulnerability that was exploited in the Heartbeat malware was specifically in something known as the Heartbeat message that is a component of the TLS library. Now this Heartbeat message is sent between the client and the server and essentially used to keep the connection alive between these two systems. So what is done over here is that one of these systems would create something known as the Heartbeat message and send that message to the other system. Over here, for example, the client would create the Heartbeat message and send that message to the server. Now the server would determine that it is indeed the Heartbeat message and replicate that particular message that it received and send it back to the client. So this is kind of a ping pong kind of thing where one system would send a message and the other system would reply with the same message. Now the Heartbeat message looks something like this. So it comprised of a 1 byte type over here, which essentially specified that this particular message was the Heartbeat message. Second, it had 2 bytes to specify the length of the payload. So therefore, since it's 2 bytes, so the payload could be anything from 1 byte ranging to 2 power 16 minus 1 bytes. And then finally, you have a payload over here, and optionally there is extra padding that is also added. So in our example over here, the payload will be hello world. The length would be 12 bytes because hello world comprises of 12 bytes, and the type would be as follows: TLS1 HP request. Now we also look at the SSL3 structure, which essentially holds the Heartbeat message. Now the SSL3 structure has a lot of elements, but the important ones with respect to the Heartbeat message are just two. One is the D length, which is defined as unsigned int, and the other one is data, which is essentially a string, unsigned character pointer. Now this data is essentially the Heartbeat message, which we have discussed earlier, comprising of the type, the length of the payload, and the payload itself. Now notice that we have two lengths that are involved in this particular Heartbeat message. One is the D length, which is present. So this D length is defined in the outer structure, and the second one is the payload length, which is essentially part of the Heartbeat message, which is part of the data defined over here in the SSL3 structure. So the D length specifies the entire size of the Heartbeat message, including the type, length, as well as the payload. But the length inside the heartbeat message, that is the payload length, just specifies the length of the payload. Now, the payload length, that is this length, is controlled by the creator of the heartbeat message. For example, if the client system has creating the heartbeat message, then the client system can decide on what is the length of the payload. Another observation we see over here is that the payload length should be strictly less than the D length. However, in the actual code of the in OpenSSL's TLS library, this check was never made. So as a result of this, what could happen was that the client system which created this heartbeat message could create or set a particular length for the payload which is very large. And since this length was never checked, it could result to a buffer overread. Since the payload length was never checked with respect to the D length, it could result in a buffer overread. So let us look at the Heartbleed attack with an example. So we have a client system over here which has created a malicious heartbeat message. So the heartbeat message would look something like this. The first is a type which is of 1 byte, which specifies the TLS HP request. The second one is the length, where maliciously the client system has filled in the maximum length, that is, since the length is of 2 bytes, so the maximum length could be 2 power 16 minus 1, which is 65535. So now over here in the payload data, the client system just fills in 1 byte, even though it has specified that the length of the payload is 65535 bytes. Now what happens during the communication is that this particular heartbeat message is wrapped in the SSL3 structure. Now the SSL3 measures the length of this message as just 4 bytes, 1 for this type, 2 for length, and 1 for this data which it has found. So thus it would specify the D length as 4 bytes. So what happens in the victim, that is our web server, is that the web server completely ignores the D length part over here and just looks at the length within the heartbeat message. Thus, what it's going to do is it's going to copy the payload which is present over here, that is the 1 byte of payload, and also it is going to, because the length is specified as 65535 bytes, therefore it will also copy all the adjacent bytes that are present in its memory. Thus the response from the victim would look like this way. It would comprise of 1 byte for the type, that is TLS HP response. The length would be specified as before as 65535 bytes, and the payload data would comprise of the 1 byte that was sent by the client machine, as well as 65534 adjacent bytes. Thus this particular packet gets wrapped in the SSL3 response, and therefore the length in the SSL3 response is 65538 bytes. So D length in the response from the server to the client is 65538 bytes. Now what is happening here is that there is a buffer overread, and the server's data present in that particular segment gets transferred to the client. And what was actually demonstrated in this Heartbleed malware was that a lot of sensitive data held in the server was actually leaked to the client machine. So we will dig a little more deeper into how the heartbeat actually works, and we will look at the OpenSSL code which actually had the vulnerability. So the important function for us is this particular function, that is the TLS process heartbeat. Okay, so we have here a pointer P which is defined, and this pointer is initialized to the heartbeat message, that is the data present in the SSL3 packet which was obtained. The next important part is these 3 statements over here, where at the server end, the server is trying to evaluate the heartbeat packet that it has obtained. The first thing that the server would do is determine the heartbeat type, which, as we've seen before, is the TLS HP request. So then it would extract the payload length, which is then stored in the payload. So this is the 2 byte length which gets stored in this payload variable present here. And finally, there's a pointer P1 defined, which points to the actual payload data. So the next thing we look at is this particular response over here, which is a call to the malloc function. So this malloc is called to essentially create the response which is sent back from the server to the client. Note the critical aspect over here is that the size requested to malloc comprises of 3 bytes plus the payload length plus the padding. Now the padding is specified as 16 bytes, and payload, since it is the payload length, and as we've seen over here, the payload length is 65535 bytes. Therefore, the size of the response is going to be 3 plus 65535 plus 16 bytes. The fourth critical point in this function is this invocation to memcopy. So this invocation to memcopy essentially creates the response from the server back to the client. It essentially fills the recently created buffer with the payload data that the client has sent. So note that even though that the client has sent 1 byte, since the payload specified was 65535, therefore the buffer would actually contain data of 65535 bytes. So out of these 65535 bytes, there is only 1 byte which contains what the client had actually sent, and the remaining bytes is due to a buffer overread where 65534 bytes adjacent to that 1 byte is copied into the buffer. Now this buffer which was just created is wrapped in the SSL3 structure and sent back to the client. Note that we are sending the buffer here, and the size of this particular packet is 3 plus payload plus the padding. Thus what the client obtains is the response to its heartbeat message comprising of just 1 byte which it actually sent, and the remaining almost 64k bytes of data which it has gleaned from the server. This particular slide shows the dump of the data which is obtained from some server. So what we see over here is that a lot of information present in the server gets leaked to the client. Many of them are critical information such as the login accounts and so on. Aspects such as the password and so on get leaked from the server to the client. So each invocation of a malicious heartbeat message would allow the client to read about 64k of server data. By repeatedly creating such malicious heartbeat packets over a period of invocations, the client machine would be able to glean almost the entire heap space of the server. So the Heartbleed vulnerability was known to the public in 2014, and it took just a few days, some 2 or 3 days, to actually fix this vulnerability and patch the OpenSSL code. As you would understand by now, the flaw or the vulnerability in the code was very minor. All that was the problem was that the D length could be much smaller than the actual payload length. So what I would like you to think of right now is to look at this code and figure out how or what statements to be added in this code so that the Heartbleed vulnerability can be fixed. Thank you.